Have you ever really thought about what happens inside a kiln? You put in a pot covered in this, gritty, chalky powder, and it comes out with a shimmering, super durable layer of glass. It seriously feels like magic. But what's amazing is that it's all pure chemistry.
So this is the big question, right? How in the world does that mineral slurry melt, fuse together, and then cool down to create those beautiful, tough surfaces we see on ceramics? That's what we're going to break down, the whole journey from a simple powder to a protective, glassy shield.
Okay, here's our game plan. First, we'll look at the basic recipe, like what's actually in a glaze. Then, we'll get to know the key players, the stuff that builds the structure and the stuff that makes it all melt. After that, we'll see how you can control them to get the exact finish you want, and finally, we'll talk about how to troubleshoot when the chemistry goes a little sideways.
So, at its core, pretty much every ceramic glaze comes down to a simple three-part recipe. And once you understand these three components, everything else just clicks into place.
Think of it like this. You've got your glass former. That's the main ingredient that's actually going to become the glass. Then you've got the stabilizer, which keeps that molten glass from just sliding right off the pot. And then the flux. The flux is the real magic ingredient that gets everything to melt at a temperature your kiln can actually handle. Honestly, every single glaze is just a delicate dance between these three.
So let's start with the most important part, the structure. These are the ingredients that create that strong, durable network that we all recognize as glass.
And the absolute star of the show is silica, or SiO₂. It's the primary glass former in just about every glaze you'll ever encounter. It creates these long, strong molecular chains that give the final glaze its hardness and durability. Now, on its own, silica makes a fantastic glass. But here's the catch. Its melting point is way, way too high for a standard kiln. It just needs a little help.
And that's where alumina, or Al₂O₃, comes in. Think of alumina as the traffic cop for your molten glaze. It's what we call a refractory material, which just means it resists heat. Its whole job is to stiffen up the mix and increase the viscosity, basically making the glaze gooey enough to cling to the side of a pot instead of dripping all over your kiln shelf. It's also absolutely crucial for chemical resistance.
Now for a really cool one, boric oxide, or B₂O₃. This stuff is a special player because it pulls double duty. It helps form a strong glassy network, just like silica, but it also acts as a flux, helping to lower the overall melting temperature. It's a key ingredient for making glazes that are both really durable and melt at lower temperatures, a real game changer.
Okay, so if silica won't melt on its own, how do we get it to cooperate inside a kiln? Well, we bring in the agents of change, the fluxes.
To put it simply, without fluxes, we wouldn't be able to make the ceramic glazes we know and love. But how do they actually work? Well, on a molecular level, they're basically little disruptors. They wedge themselves right into silica's strong, orderly network, breaking it apart and allowing it to move around and melt at a much, much lower temperature. They are the true catalysts here. But, and this is a big but, not all fluxes are created equal. We've got two main families here with very different personalities, and this is where potters have to make their first big choice. On one side, you have the alkali fluxes, like sodium and potassium. They're super powerful melters and create really bright, glossy surfaces. The catch? They have a high rate of thermal expansion, which, as we'll see, can cause some serious problems. On the other hand, you have the alkaline earth fluxes, like calcium and magnesium. They tend to produce softer, satin, or even matte surfaces, and they have a much lower thermal expansion.
And then you've got zinc oxide, which is a true wild card. In moderate amounts, it helps the glaze melt really smoothly and can even improve the fit on a pot. But if you add more, it completely changes its personality, and it starts to encourage the growth of these tiny microcrystals that create those beautiful matte and crystalline effects. So, how do we actually use this chemical toolkit to get a specific look? I mean, whether you want a brilliant, shiny gloss or a soft, buttery matte, it all comes down to controlling that recipe.
This slide really shows the two main paths you can take. For a glossy finish, you're aiming for a perfectly balanced recipe where everything just melts into a smooth, uniform layer of glass. Simple enough. But for a matte finish, your goal is actually to encourage a kind of controlled imperfection. It's a process called devitrification, where you intentionally create tiny crystals within the glass as it cools. It's those little crystals that scatter the light and give the surface that soft, non-reflective quality.
And get this, it doesn't take much to tip the scales. Just crossing a threshold of about 10% for ingredients like calcium or zinc is often enough to push the balance from a glossy melt to a crystal-forming matte. That one simple percentage can completely redefine a glaze's entire character.
Of course, with such a delicate chemical balance, things can, well, they can sometimes go wrong. So let's look at some common problems, starting with the sound you might have actually heard before.
You know that high-pitched ping sound that comes from a pot, sometimes hours or even days after it's out of the kiln? It might sound kind of delicate, but that's actually the sound of your glaze cracking. It's the most common glaze fault out there, and it's called crazing.
Crazing is all about a simple mismatch in size. The glaze has what's called a higher coefficient of thermal expansion, which just means it shrinks more than the clay body does as it cools down. So imagine trying to put a size 5 t-shirt on a size 6 person. As it cools and contracts, that glaze gets stretched way too tightly over the clay, and eventually it just cracks under all that tension.
And this chart, well, this chart just lays out the culprits perfectly. Take a look at this huge bar on the far left. That's sodium and potassium. Remember them? Those powerful alkali fluxes have the highest impact on thermal expansion, which makes them the #1 cause of crazing. Now look all the way to the right. See? Our structural buddies, silica and alumina, have super low expansion. This gives us a crystal clear roadmap for how to fix the problem.
And here's the practical fix. To stop crazing, you just have to lower the glaze's expansion so it fits the clay better. You can do that by adding more of those low-expansion ingredients like silica and alumina, or by swapping out some of those high-expansion alkali fluxes for lower-expansion ones like calcium or zinc. It's all about adjusting the recipe.
So you see, learning the chemistry behind what makes a glaze work or fail, it doesn't take away any of the artistry or the wonder of it all. Not at all. Instead, it gives you, the creator, the control to actually achieve your vision, to solve problems, and to turn that magical transformation from powder to glass into a craft that you can predict and repeat. It really does put the wand right in your hand.